Hello everyone, this is going to be a little walkthrough of the 2023 PESS 1.4, the Physics, Earth and Space Science unit, Demonstrate Understanding of Energy in a Physical System. Because this is the 2023 paper, this is technically a pilot assessment. It can still be used absolutely for your revision, and I'm going to narrate myself doing the assessment, highlighting the achieved merit excellence points for your benefit. If you haven't already, make sure you've got a pencil, a calculator, and a copy of the equations, the resource sheet to hand, because obviously they're going to be used. Here we go. Well, in case you don't have a resource sheet, it does give you all of that information here. You have to just keep flicking back wherever you are up to. So, question 1. Jamie plays with his football while he waits for his bus. He throws the ball vertically up. The ball has a mass of 0.15 kilograms and reaches a height of 3.4 meters. So I find it can sometimes help make the questions a bit easier to answer if you underline things that I think, things that are important. So we've got a distance, but we know it's a height rather than just a distance, and we've got a velocity as it lands as well. Now part A is asking us, in the box below, write an equation to show the energy changes taking place when the ball falls back down from its highest point. Now when it's at its highest point, we have lots of gravitational potential energy. Because it's above the ground, we have gravitational potential energy, and these boxes are not big enough. Good Lord. Now by the time the ball has reached the floor again, it's been moving, and so it has kinetic energy. And our last one, at the moment it hits the floor, it has been pushing its way through air, and so there will be some thermal energy as a waste form of energy. Okay? Now for achieve, you have to just say those three answers basically. There are no other ways of getting the credit there. Part B though. Calculate the size of the average force of friction between the ball and the air. Begin your answer by showing that, on its way down from the highest point, 0.537 joules of mechanical energy are changed into other forms of energy. Now, essentially what's going to happen here is you're going to do two calculations for the gravitational potential energy and for the kinetic energy in order to work out what the thermal energy is, basically. So, in order to work out what the thermal energy is, I'm going to work out the GPE and the kinetic energy and take the kinetic away from the GPE. Sort of treating this like a rearranged equation, taking away this from both sides will leave me with my thermal left over. Okay, so my gravitational potential energy is calculated using the equation mgh from your equation sheet. Up here. mgh. The mass of the ball was 0.15. It's one of those things we underlined in the very first part of the question up here. Gravity is 10 according to the information at the top of the page, and the height that the ball had was 3.4. So then you simply work out what that equals. 0.15 times 10 times 3.4. And so there were 5.1 joules of GPE. Now for the kinetic energy, again using the equation at the top of the page, half mv squared. The mass is still 0.15, and we are told that just before it hit the ground, the ball had a velocity of 7.8. And so that's our velocity, and remember that the velocity is squared. So then we type this into a calculator, 0.5 times 0.15 times 7.8 squared, being careful that only the 7.8 is being squared. And you should get 4.5, ooh, no need for the second decimal place, 4.563 joules of kinetic energy. Then to work out the leftover energy, I'm just going to take them away from each other, like I'd said I'd do up here. 5.1 minus 4.563, and should always do it in a calculator to make sure you are getting the right numbers, to get 0.537 joules. Now, this matches the amount that we were suggested we should get. This is technically thermal energy. However, it's not going to make sense for us to use the equations that are labelled thermal energy here, because we don't know any latent heat, we haven't been given the specific heat capacity, and there are no temperatures mentioned. We're going to use a slightly different one. We know that the ball has fallen by 3.4 meters, and we're asked to work out the size of the force acting on the ball. So if we know that there's been 0.537 joules of thermal energy done over a distance of 3.4 meters, we can use our work done formula to calculate the force. So skipping all the way back down to the bottom of the page, I know that work done is equal to force times distance. Therefore, if I divide both sides by d, my force is equal to work done divided by the distance. The work done is 0.537 and the distance was 3.4. Therefore, I can calculate the average force of friction to be 0.15794 dot dot dot, and then I'll round my answer to 0.158 newtons, like that. Now, if you did all of this all the way through and got your answer down here, that would give you excellence. If you make one sort of really big mistake, but still follow your working through and get a slightly different answer, but you have done all these steps correctly, or tried to, with one mistake, then you can get merit. Or, if you've got up to this point here, ignoring the work done section, if you work out the difference in the two energies, that's enough for merit. If you work out any one of these two energies up here, either one, GPE or kinetic energy, that gives you the achieve. Okay? All of it together is excellent. Part C. While falling, 80% of the 0.537 joules is converted to other While converting, 80% of the 0.537 joules converted to other types of energy is absorbed by the ball. The specific heat capacity of the ball is 8,200 joules per kilogram per degree Celsius. Calculate the rise in temperature of the ball as it falls. Okay? Now, we know, well, we've been told that 80% of the 0.537 joules is absorbed by the ball. We are then told to work out the rise in temperature of the ball. So first things first, I'm going to work out 80% of 0.537. To do that, I'm going to multiply 0.537 by 0.8. Type that into a calculator, and you get 0.4296 joules absorbed. Now we're told the specific heat capacity, and we are asked to calculate temperature. So we have energy, we have mass, we have specific heat capacity, and we're looking for temperature. So we're looking for one of these formulae that involves all of those. We've just worked out how much energy was absorbed, thermal energy was absorbed. The mass is given to us in the question, 0.15, and we've just been told C, so we can work out delta T. So first things first, I'm just going to write down the equation E thermal is equal to mc delta T. Now I want to get temperature on its own, so I'm going to divide both sides by mc. Therefore delta T is equal to E thermal over mc. My E thermal is 0.4296, my mass was 0.15, and my heat capacity was 8,200. I'm just going to do it all in the calculator, save me a job doing it individually. 8,200. And so, we've got a very, very small answer of 0.000349, which we can round to 0.00035 degrees Celsius. Oh, sorry, I should go to three significant figures. 349 degrees Celsius. So you should always try to match the information in the question. Because this is given in three significant figures, I should give mine in the same. Okay. If we did all that, we get merit. If you just worked out this percentage, that's enough for achieve. Or if you tried to do all this and made one big error, you can still get achieved for it. Altogether, this is your final answer. You get merit. Now, part D. After some time, Jamie's bus did not arrive. Jamie shoulders his backpack and walks to the train station. On his way to the platform, he climbs a flight of stairs. In terms of work and/or energy, explain why each of the following three statements given below is true. No calculations are needed. So we've got three different images. Looks like he's stationary in I. Looks like he's walking horizontally in part 2. And then it looks like he's walking up a flight of stairs in part 3. Part I's sentence says no work is done on Jamie's backpack when Jamie is standing at the bus stop. Because we're talking about work done, I'm just going to quickly write down the equation for it here to remind me. If he's standing at the bus stop, he isn't covering a distance d. Because he is standing his 0 meters. There is also no movement horizontally, so no kinetic energy. So this isn't a question about just work done, but there is, it's one aspect of this. And I suppose maybe I should have been more clear with my first statement. Because he is standing, his distance is 0. I want a little asterisk and complete my sentence a bit better. He is standing, his distance is 0, therefore there is no change in GPE, in gravitational energy. I should have been more specific the first time. Okay? Now, part 2, no work is done on Jamie's backpack when Jamie walks at constant speed on horizontal ground. So, if he's walking with a constant speed, it means that his kinetic energy is staying the same. Because kinetic energy is half mv squared, if his velocity is staying constant, his speed, that means his kinetic energy is. So, constant speed means constant kinetic energy. And then because he's moving horizontally only, it means that there is no change to his gravitational potential energy either. So horizontal motion means no change in GPE, same as part I. Then we go down to part 3. Work is done on Jamie's backpack when Jamie climbs the stairs. If he's climbing the stairs, when climbing stairs, the store of GPE increases. A force is being provided over a vertical distance, so work is done, as work is equal to force times by that distance. Okay? Now if you describe all of these 3 scenarios out like the way I have here, that's enough for excellence. If you do 2 of them to this level, that's merit. And you either, for achieve, have to discuss the kinetic energy and gravitational potential energy in one of these examples, or if you just make very quick statements. So this idea here that the distance is 0, therefore work done is 0, if you just left it at that bit there, that would have been enough for achieve. If you'd said here that there's just no force, no change in, well, he's not having to overcome a force, sorry, because he's just walking horizontally and there's no horizontal forces that we've been told about, then that's achieved. And if you just say that he moved upwards and there was a gravitational force, then that's achieved for that one. If you do all 3 of them fully like this, discussing your kinetic and GPE, that's excellent. Now this question, it is quite vague. It doesn't specify which energies you need to talk about, but it is expecting kinetic and GPE to be talked about. Because he's moving upwards, or moving at all, those are the 2 energies that are involved. Okay, question 2. This one's about electricity. And we're told that Jake has a torch that uses 3 1.5 volt batteries in series. The torch has 2 lamps, each rated at 4.5 volts, connected as shown in the circuit diagram below. The current through each lamp is 0.5 amps. So, first question is asking us to calculate the resistance of each lamp. We've been told a series of voltage and current values. So when we look at this equation sheet, we're looking for an equation that relates voltage, current and resistance. Ohm's law, V equals IR. Now we want to calculate the resistance of each lamp, and so we're going to rearrange this to get R on its own. So I'm going to divide both sides by I. Therefore R is equal to voltage divided by current. Now we're told that each lamp has each lamp is rated at 4.5 volts, good lord. And so I can put 4.5 in as my voltage, and then I'm told that the current through each lamp is 0.5 amps. If you type that into a calculator, you should get a resistance of 9 ohms, remembering our Greek letter omega for the units of resistance. Okay? Now, if you did all that, that's an achieve. Part B. The batteries power both lamps simultaneously. Explain why both lamps glow with their rated brightness if connected as shown above. Begin your answer by identifying what type of connection the above diagram shows. So, It's giving you a bit of a clue here as to what you need to talk about. Begin your answer by identifying what type of connection the above diagram shows. This is a circuit where we have two different routes for the electrons to travel around in. Therefore, it's a parallel circuit. There's more than one loop connected. So we can just say straight away, this is a parallel circuit. Boom. Therefore, each loop will receive the same voltage as supplied by the batteries. Remember that that's one of our rules for parallel circuits. Current gets shared between each loop, but the voltage, each loop has the same voltage as the power supply. Okay, so if this is 4.5 volts, each loop experiences 4.5 volts. Okay, so each loop will receive the same voltage as supplied by the batteries. Therefore, they both receive 4.5 volts. This is the same as what they are rated as. In the question at the top, we're told that each lamp is rated at 4.5 volts. Okay? And so that's what they're rated as, therefore they will glow with the correct brightness. So they will have their expected brightness. Okay? Now, if you have just said that there's a parallel connection, that is enough for achieve. So if you just write those first 5 words, or just write parallel circuit, that's achieve. If you describe the fact they're both receiving the same voltage, that's an achieve in itself. But if you do all of this, saying it's parallel, they get the same voltage, therefore they get their full brightness, that's merit. Okay? Now, part C. Calculate the amount of electrical energy used by both lamps in 2 hours. Begin your answer by calculating the power output of each lamp. If we go back to our equations, we want an equation that relates, we've got lots of voltages and currents, and we're looking for a power equation. And so we're going to use this equation here. Power is equal to voltage multiplied by current. So, if power equals VI, then the power of one bulb, is going to be 4.5 volts multiplied by 0.5 amps, which equals 2.25 watts. But now there are 2 bulbs, because there are 2 lots of these bulbs, there's going to be 2 lots of this power being used. Therefore, 2 times 2.25 takes us back to 4.5 watts again. Okay, so now we've got our power used by both bulbs. We're told that both lamps are used for 2 hours, however, and we need to work out the amount of electrical energy. So now that we've got our power, we need to use an equation that relates power, time, and energy, which is this one here. Energy is equal to power multiplied by time. So if we go back down here, energy is power multiplied by time. Our time, though, is given to us in hours. We can never use hours in these sorts of calculations. We have to always use seconds. Now, if you think about what's inside an hour, in 1 hour there are 60 minutes. So 2 hours equals 2 lots of 60 minutes. And inside each minute there are 60 seconds. And so we can do 120 times 60. Whoops. To work out that there are 7,200 seconds in 2 hours. Now we've got our time in seconds, we can then go back to this equation. E is equal to 4.5 multiplied by 7,200. And you work that out in your calculator to find an energy of 32,400 joules. Now, if you do all of this correctly, that's excellent. If you work out that each lamp has a power of 2.25, that was all you had to do for achieve. That was the only thing you could do to get achieve. If you then doubled that to 4.5 watts, that would be enough for merit. If you do all of this with one mistake, that leaves you with merit as well. And if you forgot to double your power rating, so you only worked out the energy used by one light bulb, then that's also merit. So if you got 16,200, that was also merit. You do all of this together though, you get 32,400 and you get achieve. You get an excellent. Now part D. Jake's torch uses incandescent lamps. These lamps have a very thin tungsten wire called a filament. When a current passes through such a filament, it heats up and glows. And we've got a diagram showing the filament at the centre of the light bulb. Now we're told that tungsten is a metal with a very high melting point and a relatively small specific heat capacity. The very small diameter of the filament means that the filament has a large resistance. Explain why the high melting point, small specific heat capacity, and large resistance of the filament are important for the incandescent lamps to work well in a circuit. Okay? Begin your answer by describing the energy changes that occur in the filament when a current passes through it. So we'll take their advice and we'll start by describing what happens in terms of the energy transfers, or energy changes, sorry. When a current passes through the filament, electrical energy or electrical potential energy is converted into heat and light. The incandescent bulb that we're talking about here is an old-fashioned one, which if you touch they do feel very hot when they've been on for a while. And obviously because it's a light bulb, it's giving out light energy. Okay? Now, whenever you're given these sorts of bits of advice by the exam, you should always do it. It's usually enough for achieve in itself. The rest of this answer it's quite long, but yeah, it's not too bad. It makes sense. So, we've got to go through and explain why the high melting point, small specific heat capacity, and large resistance are important. So as we go through, I'm going to tick them off one by one, because this is essentially a list of things to do. So why would a high melting point be important for this lamp to work in a circuit? Now, if we're converting lots of energy into heat, and we have a high melting point, the high melting point makes it very difficult to melt that filament. If the filament got broken, if it melted, let's say it melted in the middle, it would break the circuit. Therefore, the light bulb wouldn't turn on and the rest of the circuit wouldn't work. The bulb would be broken. So, a high melting point is important, essentially, so that the metal doesn't melt. The high melting point is important as it prevents the filament from melting. If it did melt, the circuit would be broken. There would no longer be a complete path for the electricity, for the electrons to flow around. So, if it did melt, the circuit would be broken. That's why it's a bad thing. Okay? So, we've discussed that one. Now, we're going to look at the small specific heat capacity. Now, it might be a good idea, it might be helpful, just to remind yourself of what specific heat capacity is. SHC is the amount of energy required to heat up 1 kilogram of a substance by 1 degree. Now, even if you're not sure how to then discuss specific heat capacity, if you've written down what it means, there might be enough in that definition that you can sort of give yourself a bit of a clue going forwards, might remind yourself or give you a bit of an idea of what next to write about. But if we have a very small specific heat capacity, it means that you don't need much energy to heat up the substance. Okay? What that means is, even if you only give it a small amount of electrical energy, the metal will still heat up. And the whole way that these light bulbs work is that they are made, the filament's made to be so hot that it starts to glow. It's glowing, well, orange hot to begin with, and eventually white hot, which is why we have light bulbs the colour they are. So, SHC is the amount of energy required to heat up 1 kilogram of substance by 1 degree Celsius if the filament, sorry, it's an ant, if the filament has a low SHC, it does not require much energy to be heated up. Light bulbs give out light when they're hot. Well, I should say incandescent bulbs do, not newer ones. But this question is about the older ones. So. Light bulbs give out light when they're hot. So this reduces the electrical energy required. Okay, so again we're linking it to the actual use, not just describing what it means physically. We've discussed our small specific heat capacity. Nice. Now, the large resistance of the bulb. Why is that useful for for a light bulb to work in a circuit? Now, a large resistance, if you remember the pencil that was made to catch fire, because the graphite at its centre has a very high resistance, the higher the resistance, the more collisions there are between electrons and the metal atoms in the filament. If there are more collisions, there's more thermal energy being transferred to the filament, and therefore it's going to get hotter quicker. And so a large resistance means that more electrical energy is converted into thermal energy and therefore light energy or radiant energy. Okay? Now, if you have discussed all of the points in the depth that I have, that's excellent. The mark scheme says you've described the energy change correctly and you've stated and reasoned at least 2 of these points with clear links. So you didn't have to do all of this, you had to just do 2 of them. I lied. So this first sentence is needed for excellence, but then any 2 of these discussed and linked to its actual use, and not just saying that more energy is converted, less energy is required here, but this reduces the electrical energy that's used, is the link. If you did this for just 1 point with clear links, that's merit. And if you just did this first sentence discussing the energy change, then that's achieved. Or if you just did one of these, that's achieved. Sorry, I missed one of the things for the excellence ones. If you did forget this very first sentence about the energy transfer, but you did do these 3 paragraphs, you can still get excellence based on those 3. If you just did 2 of them without the first sentence, then that's merit. There you go. Question 2. Okay, question 3. Pearl has had an air conditioning AC unit installed in her room. The AC unit uses electricity to cool down air and blow cooled down air into her room. This way, Pearl's room is comfortably cool although it is hot outside. AC units are typically mounted high up on a wall. In the diagram below, draw labelled arrows to show the movement of warm air and cool air in the room. Disregard effects of air being pushed out of the AC unit. So we haven't got to worry about the wind effect from it blowing, but if we are depositing cold air here at the bottom of the AC unit, the cold air, because it's an air conditioning unit, it's cooling down air, that colder air is less expanded. It's got a higher density, Therefore, the cold gas sinks. So you can say cold air sinks. Because the cold air is sinking, it then pushes warm air to rise. So we've got an arrow showing the movement of warm air and cool air. That's it. For achieve, you had to have both arrows going the correct way with a label to say which one's which. If you used colours, I presume red and blue you'd get away with it, but I would always label it as well just to make double sure. Okay. Now part B, the volume of space occupied by a given amount of air depends on the temperature of the air. This is the reason for the movement of warmer and cooler air around the room. Explain in terms of particle theory of matter why a given amount of cooler air occupies a slightly smaller volume of space and the same mass of warmer air. So this is going way back to the solid, liquid and gas diagrams and what we said the different movement of the particles is like. Now, we're talking about gases only here because it's the air of a room. We're not talking about it condensing into a liquid. But we are talking about the temperatures. So, in cooler air, what can we say about the vibration of the particles compared to hotter ones? In cooler air, particles vibrate less as they have less energy. This means that they do not spread out as much as warmer air. Therefore, cooler air will occupy a smaller space. Just like that video of the balloon we saw where they poured liquid nitrogen, I think it was, onto the balloon, and because it cooled down the air in the balloon collapses. As it heated back up again, the balloon expanded the air, stretched the balloon out again. If you make both of these points and they don't spread out as much and they vibrate in less, they're less energy, that's merit. If you just say one of these points, then that's achieved. Okay? C. One summer morning, Pearl checks the room temperature on her phone. 2 minutes after she starts the app, she sets the AC unit to 18 degrees Celsius and switches it on. The temperature in her room drops as shown in the graph below. Pearl's room contains 41.4 kilograms of dry air. The specific heat capacity of dry air is 718 joules per kilogram per degree Celsius. Using information from the graph above, calculate the average power of the AC unit in the 2 minutes after Pearl sets it to 18 degrees. Begin your answer by calculating the amount of thermal energy drawn from the air in Pearl's room. Okay, there's a lot going on here. So this graph is showing the temperature of the room and the time since Pearl started the app. And it took her 2 minutes after starting the app to turn the AC on. So once Pearl has set it to 18 degrees, that starts at 2 minutes. And it then finishes at 4 minutes. So we're going to see what the temperature change was at those times. Now I'm going to get a ruler out so I can draw it nice and clearly, and a pencil. Now, with this graph it's quite obvious where the lines are, but in future, for other ones it may not be. It's always a good idea to draw with a ruler, starting at the axis, starting at the 2 minute mark, all the way up to the line. Okay? And then same again for 4 minutes. Now, wherever your lines upwards reach the actual graph line, we're going to draw a horizontal line across, and it's only just long enough to reach. And then we'll do the same thing here. Now, it was quite clear to begin with, but it started at 22 degrees and it ended at 18 degrees. For other graphs that might not be so clear, you should be drawing on it, especially if it says use information from the graph above. I don't care how obvious the lines make it, you draw something on there, because often that's part of the mark scheme is the working done. Have you drawn lines on the graph, etc. It makes it really clear how you're getting your numbers. Okay, so it started at 22 degrees and it ended at 18, so our delta T is going to be 22 minus 18 equals 4 degrees Celsius. Now we're told to start our answer by calculating the thermal energy drawn from the air. And from that front page, the E thermal is equal to mc delta T. We were told that there was 41.4 kilograms of dry air. That's our mass. We were told the specific heat capacity was 718. And we have just worked out that the temperature change was 4. And so, I'm going to just work out what that answer is. 41.4 times 718 times 4 is 118,900.8 joules of thermal energy. Okay? If we stop there, that is a merit answer. If you made a mistake in doing that, that's achieved. In order to get onto the excellence grade, you have to use the power equation. Calculate the average power of the unit in those 2 minutes. And from the first page, our power equation that relates energy and time is this. We want to get power on its own, so I'm going to divide both sides by T. Energy divided by time. Now the time taken for this to happen, we've just worked out our energy change up here. The time taken was 2 minutes. But just like before, we have to change that into seconds. Now 2 minutes, there's 60 seconds in a minute, so there's 2 lots of 60, 120 seconds. And so our equation becomes 118,900.8 divided by 120. Put that in a calculator and you get 990.84 watts. I'm going to round it to 991 watts. If you do that extra step here, that's the excellence point. Everything above was merit, and for achieve, if you made a mistake in working out this 118,000, then you get achieved. So if you made a mistake with your temperature calculations, you can still get achieve if you go all the way up to calculating this number here. Okay. Part D. At night, when it gets cold, Pearl closes the curtains on the windows in her room. Pearl's curtains reach down to the floor and are close to the wall. Explain why the layer of air between the curtain and the window reduces heat transfer by conduction through the glass of the window pane. In your answer, you should explain in terms of particle theory of matter, how heat transfer by conduction works. And then we should compare and contrast conduction through air and glass. So, the way that conduction works, again, we should start with what it suggests. Explain in terms of particle theory how heat transfer by conduction works. So, heat transfer by conduction requires two substances to be in contact. Now, it doesn't have to be two solids, which is a bit of a misconception sometimes. It can be a liquid and a gas, a liquid and a solid, or a gas and a solid. If you walk into a sauna and it feels very warm on your skin, that's because the warm air that's been in the air that's been heated up is conducting heat onto your skin. Same as if you spill a cup of tea on your skin, it hurts because it's conducting that heat. So heat transfer by conduction requires two substances to be in contact. The warmer material's particles vibrate with greater energy. They vibrate into the neighbouring substance, transferring thermal energy to the cooler substance. So this is why they have to be in contact. If this is one particle, my finger is vibrating back and forwards, and I put a cold substance on it, it literally is knocking into the other finger, transferring energy until they both have both have a greater energy than the cooler one did to begin with. Okay? So they vibrate into the neighbouring substance, transferring thermal energy to the cooler substance through collisions, or transferring thermal energy to the other substance through collisions, so literally bumping into each other. So now we've explained how heat transfer by conduction works. We now need to compare and contrast conduction through air and through glass. So thinking about the states of matter of air and glass, glass is a sort of, well, for all intents and purposes, a solid, and air is a gas. Therefore, we're going to describe the difference in the particles between solids and gases. Particles in glass are very close together, as it is a solid. Glass isn't actually a solid, it's a very, very viscous liquid, which is why old windows will sometimes sag, but we're going to say it's a solid for all intents and purposes here. Particles in glass are very close together, as it is a solid. Air particles are very spread out, as air is a gas. Conduction occurs much more slowly if the particles are spread out, as collisions therefore thermal energy transfers occur. I don't know how many C's I've drawn there, I've drawn far too many. Occur much more infrequently or less often. Okay, so because the gas particles in air are very spread out, it takes a while for the warm room to conduct with the air particles. Because they're so spread out, they're not far less likely. Oh, sorry, I need to move this up. Sorry. So air particles are very spread out, as air is a gas. Conduction occurs much more slowly if the particles are spread out, as collisions, and therefore thermal energy transfers, occur much more infrequently. They're not just likely to happen. And then you can also add the sort of opposite, the vice versa point. In a solid, collisions, oh no, sorry. Glass is a solid, so conduction can occur rapidly. Therefore, air acts as a thermal insulator. Okay? Now, if you make the point that conduction requires two different substances, one of them has a greater temperature, higher temperature, it's warmer, it vibrates, its particles vibrate faster or with more energy. One of those points is an achieve. Sorry, no. I've misread the mark. This mark scheme is a bit convoluted. Sorry, for achieve, you had to say somewhere that conduction works by particles vibrating into one another, or that the particles in air are much more spread out than a solid, or if you just say air is a thermal insulator here, that's enough for achieve. If you say any of two of those points, that's merit. If you say all three and they're in depth enough, in the same way I think mine is in depth enough, that's enough for excellence. Okay, so if you make the point that conduction occurs through collisions and particles are more spread out in a gas, therefore air is an insulator, that should be enough for excellence. Two of those points is merit, one of them is achieve. And that's the paper.